The question that we have here is, or maybe we before starting any kind of mining is that can we make money out of this pile of rock, right? That is why we need to do some kind of reserve estimation, right? So before going for this mining, this was all covered with the topsoil and nothing was there, right? So first thing is to estimate what is the quantity of this like the ore that is present there. And to do this thing, I'll quickly revise your concept here. First thing we go to the site and do some kind of physical observation, what kind of mineral is present, right? And then in this case here, we will do some trenching to see the mineral content, or maybe we go for like this satellite survey kind of thing where we get reflection from different kind of minerals and to see. Yes, somebody wants to say something. Okay. So, and then, or maybe we can go for aerial survey, right? Like we put the geophysical sensors in the aeroplane and do the survey of the area. And then finally, what we do is, we go for drilling, right? Take the core out of it and investigate what kind of mineral is there, where it is present, how much it is present, right? So, and these are the core, core taken from outside, right, to investigate what are the different percentage of different uh, ore or whatever it is, right? And if you see one of the borehole lithology, this looks like it. So if you take the core out and you join all of them, maybe this is done for this whole mine, right? So you can see clearly some coal bank that is going or maybe there in the boreholes. So like these are all different boreholes. Like maybe we made some 6 boreholes here, right? And we can clearly see the thickness. Like for example, the picture quality is not good. So in one case, it is saying 81.7 to 87.65 or something like that. So it's around 6 meter of coal. So we do these kind of things to estimate, or maybe the thickness or grade of the mineral present. Okay, so but the issue is this deposits are huge. I just wanted to put this thing here. The Tata Steel holds Noamundi lease over an area of 1160 hectares in West Singhbhum district of Jharkhand, right? So this is close to, this is if you calculate in if you see in kilometer square. So this one of the mine can be in this range, right? So so maybe it is 3.5 kilometer by 3.5 kilometer. So and we cannot do a scan of this whole area in all the points, right? Like this is not possible. So what we do is we drill holes in a in some specified distance, and we have some norms for that. We'll be talking about this UNFC norms, or maybe we talked in our metal mine class. So and if you see one of this, right, that for let's say bauxite or chromite, the distance would be around 100 to 300 meter between two boreholes, right? So this is in our maybe in our detailed exploration. So let's say this is the area where we have our bauxite deposit, and this is 100-meter pattern grid we have made. Maybe I don't know. So 100 meter by 100 meter pattern grid we have made, and what we need to do is between this 100 to this 100 meter distance, we don't know what is happening here, right? So we somehow need to use some technique to get the changes in grade and the thickness all around this area. Is this clear up to here? Like, anybody wants to ask anything? Anyone? Okay, so I think it's pretty clear. So there are two ways to do that. From this borehole information to getting the total quantity of the ore or mineral present in that area. So we use two techniques. One is traditional method, and second is geostatistic method. Okay, so today we will be talking about this traditional method. How do we do that? And geostatistics method will be like, which involves kriging all and all. So in variogram. So we will be talking about this thing in our next class. So there is something called extension function. I'm sorry. So as you can see, this extension function is defined as a technique used to extend sample values to estimate the value of surrounding volume of the mineral body. What it says is, it's a function. So if you know the value here, how can you get the value at a different location, right? And these extension functions are based on three main principles. One is rule of gradual change. Mani, are like anybody have you learned about these things in any other classes? Rule of nearest point, rule of generalization.
No, sir.
Okay. So we have three rules that we use, right? First is let's see one by one. So first is rule of gradual change. So what this rule of gradual change says is is termed as the law of linear function, is based on the assumption that all sample elements of a mineral ore body changes gradually and continuously as a function as a linear function along the straight line connecting two adjacent sample points. So let's say we have one borehole here, we have another borehole here. So let's say the grade of the ore is 1.2 here, and this is, let's say, 1.6 here. And if the distance is let's say L0, so at a distance L, if you want to get the grade of this ore, that how you can find it out. So this is changing from 1.2 to 1.6. So at distance L, this will be 1.2 plus what? Can anybody guess? Anyone? What will be the grade at let's say point A is 1.2, point B is this, and
0.4
at point B.
0.4
L
by
by L
L
naught.
naught. Yeah, L by L.
Yeah, 0.4 by L naught into L, right? So 1.6 minus 1.2 is the difference divided by L naught into L. So this is the rule of gradual change. Similarly, for like the most of the cases that the thickness of this, if you drill a borehole and you find from this depth to this depth the ore, then this thickness is not constant. Maybe if you drill another hole, this will be from maybe this one, this to this. So this T1 thickness here, and this is T2 thickness here. At point, this is point A, this is point B. So in that case, it's changing, right? It's increasing. So maybe so similarly for uh, same rule applies for the thickness also when we try to calculate. Is this clear? Anybody who does not, I would not understand.
Sir, can you repeat this concept again?
Okay, so the problem is, like as I said, let's say our ore deposition is here, right? And as I said, in case of Noamumbi mine in Tada, it is around 11.6 kilometer square. So first thing is we cannot scan the whole area each point by point, like we cannot drill the whole area, right? Like we cannot do that. So what we do is in our detailed exploration, like we drill holes as closely as possible. Okay, so from here at each point we know what is the thickness and we know the grade. Now, when we calculate, we try to calculate what is the total amount of the ore in this area, then we need to apply some kind of, or maybe we assume something, right? So one of the assumption is says like gradual change, rule of gradual change. Okay, and it says so. This is what I was trying to explain. At point A, the grade is 1.2. Okay, so 1.2% or whatever. So, and at point B, the grade is 1.6, right? So, and this rule of gradual change, what it says, at point P, which is at a distance L, you can calculate using 1.2, which is the grade at here, this point, plus the difference in grade, which is 1.6 minus 1.2, divided by total distance L0 into L. Okay, so this will give you the grade at point L0. Similarly, for the thickness. Is this clear? Okay,
Yes, sir.
but maybe it is like in the real case, let's say this comes out to be 1.36. Okay, or 380. So maybe in real case it should be like it can be 1.4 also, right? And or maybe 1.28. Nobody knows, but we just assume that this is how it varies. Is clear?
How that thickness is increasing?
This is the thickness of the deposit, right? Like let's say in here, in the location, let's say the first borehole is here and second borehole is here, right? So maybe the thickness of the ore body is 103 meter here. It can go like 101 or maybe 160 meter here. Who knows, right?
Okay, sir.
So up to what depth this ore body is like ore is coming. So it's not like it's going through and through all the like all the way down, right? Like so it has some thickness.
Yes.
Okay, yeah. So if we what I'm saying is if you want to get the thickness of the in between, so you use that linear interpolation kind of thing, right? Yeah, similarly, there's something called method of triangle. So in this method, all boreholes are connected to one another by a series of straight lines, thus dividing the ore body into series of triangles. Okay, so what it does now we know that at a point you can calculate using this, but similarly we use the method of triangle, right? Let's say these are the borehole locations. In this case here. So to estimate the total quantity, what we do is we divide this in triangle, join the nearest point. Okay. So in this case, you can also join this point with this point, right? Can you do it like that? The green one. And join this with this one. Anybody?
Yes, sir, but maybe like we are connecting the nearest points, I guess.
Yeah, so the rule says try to make it equilateral, as much equilateral as possible. Okay, so we will have different kind of quantity measured in two cases. So it should be like an equilateral triangle. Okay, as much as possible. And then we have some formula that I will talk. Wherein the altitudes of the vertices represent the verifying thickness of the mineralization. Each triangle represents the base area of an imaginary prism of some thickness. And like to get the average grade, let's say we have 3 points here and we connected with a triangle, and let's say this the grade is G1, right? And this is thickness is T1 here. This is G2 and thickness is T2, and this is G3 and thickness is T3. Okay, then you can calculate the average grade as this. Okay, G equal to, for this triangle. For this triangle, the average grade is G1 into T1 plus G2 into T2 plus G2 into T3 into T3 plus T1 plus T2 plus T3. Is this okay? And then can anybody tell me, if you want to get the quantity of the ore, how can you find it out? Anyone? Can you hear me? Anybody?
Yes, sir, you're audible.
Yes, sir.
So
Okay.
maybe we find the area of the triangle and then multiply with the grade and then take the average by dividing the whole area of the plot.
Okay, so let's just do one thing.
So,
Yes.
can you tell what each vertices represent basically?
So these are the boreholes. So let's say what I said was, like this is the area where the deposit is there. So you drill the boreholes, right?
Yes, sir.
So these are the location of the boreholes. Okay, and when you did that, put that borehole, and you found out that the average grade is G1, and the thickness up to which the mineralization has occurred is for T1. So I showed one of the borehole, and maybe you can find out that okay, this is your ground level, and up to here nothing was there. Okay, maybe some different kind of waste or rock was there, or different kind of rock was there, and here is the ore, let's say. Okay, so this is the ore. Maybe you can change the color here. So red is our ore. So you take this ore to your lab, do some kind of investigation to find out what is the average grade. Okay. Also, when you take out this ore, you know up to what length this mineralization has occurred, right? So this length is your thickness T1. This is what I'm saying. Is this clear?
Yes, sir.
Okay. So let's say we have one, like triangle here, and I'm saying that this is 0, 0. The coordinates of these vertices are 0, 0, 60, 0, and this is, let's say, 29.1 and 73.8. And the grades are 0.6, and the thickness is 12 here. This is 0.65, thickness is 10.5 here, and this is 0.8, and thickness is 12 meter. So can you calculate what is the quantity of ore here? So all are in meters, okay? And let's say this is gram, this is gram per meter cube. So we are exploring some gold kind of thing, and this is what we got.
So the grade is coming out to be 0.685.
Okay, and what is the total quantity of gold?
So total, one second. So if we like multiply the grade with the average depth, it is coming out to be 7.87.
Yeah, so that, and also you need to calculate the area, right? To calculate the volume.
Yes, sir, and we have to calculate. Yeah. We have to bring out the area also. So and that like how are we going to calculate the area from this given data?
This is a triangle. Can we just calculate half base into height?
Acha,
After
okay,
taking
the
the
coordinate is
triangle
also
shape,
given.
how?
Coordinate is also given. Okay.
Yes.
So that T should be averaged out, na, for that multiplication with the area, then finally with the grade.
Yes, yes, yes. So what is G? Average grade. This comes out to be 0.68, you said?
Yes, 0.685.
685.
So total grade like total amount is coming out to 17,420.
17,420 gram, right?
24, yes, sir.
Okay, not bad. Some 17 kg of gold we got. Okay, so anybody has a question? Yeah. So everybody like got this answer, or who said?
Sir, sir,
yes.
explain it one more time, sir.
Okay, so yeah, so the first thing is to calculate the average grade, right? So average grade, we can use this formula, right? G1 into T1 plus G2 into T2 plus T3 into T3 divided by T1 plus T2 plus T3. So if you see the average thickness, T average equal to T1 plus T2 plus T3, right? Divided by 3. So we know the average thickness, okay, and we know we have to calculate. So this area of this triangle. So what this area of the triangle is half base into height, right? So this height, you know the coordinate, so area equal to half base into height. So if I'm not wrong, this comes out to be 2214
Yes, sir.
meter square. Okay, so you just, what is the average thickness?
11.5.
11.5 meter. So you just multiply. So total quantity is G times T times area, and this should come out to be like this. Is this clear? Okay, but you know what happens? It's just for one maybe triangle. So if you see some square kilometer areas, you have many of these triangles. So it takes a lot of time to calculate. Okay, but the concept is like this. This is what we use. I believe it's clear, right?
Yes, sir.
Okay. Next is our geometric method. This is similar to the previous one. So in geometric method or cross-section method for estimating mineral inventory is also based on the principle of gradual change. So same gradual change principle we apply. So in this case, you know what we have is we have different cross-sectional area. So we from these our maybe these are our boreholes, right? So from here we try to make a area here. Okay. So, yeah, and how do you get this area, anybody? So, because these are the boreholes, right? Anyone?
We might have estimated that area from the borehole distributions.
Okay. Yeah, so let's say you have your area A1, A2, and A3 here. Okay, so we need to apply some kind of, like concept to get the area from this borehole. Like we'll be, for one of those things, we'll be talking about the kriging and all, right? Like the geostatistical method. So let's say you have your area A1 here, A2 here, and A3 here. Then this geometrical method, what it says is pretty simple. Like the mineral area, every section is determined. First A1, A2, A3 are determined. Average value of the each section is computed by using the length weighted sample value average. Okay, I'll explain what is that. Volume of each block is computed, and volume of the block enclosed between A1 and A2 separated by the distance L may be computed as this thing. So this is the first block, let's say this between A1 and A2. Okay, so if you want to calculate what is the volume of this ore or there, then you can calculate using the average value of the area A1 plus A2 by 2 into the distance between two cross sections. Okay, and the total tonnage can be calculated using T equal to A1 plus A2 into length. So this is the initial volume times F. F is tonnage factor. Tonnage factor in tons per meter cube. Okay, so if you have some iron ore of this ton per meter cube, so then you can calculate using what is the total tonnage. Okay, so similarly, you just calculate the value for all the blocks and get the sum, right? Summed up. Is this clear? It's similar to the previous method. It's just like the area we are taking. Yes.
Yes, so sir, how is that tonnage factor determined? Like it is different for all the ores, or like in a single plot it is different for different areas?
Yeah, if it is different, then you need to, again change it, right? So maybe let's say this tonnage factor, this is the first cross section, second cross section. So this is T1, you are saying this is T1, this is T2, and this is T3, right? So T1 plus T2 by 2, you have to do it, and that tonnage factor you have to multiply for this area. Okay, so T2 plus T3 by 2, you do that and multiply with this area. If it is changing, if it is constant, then you just multiply with T or maybe F. Sorry,
Yes,
this
sir,
is
and
F.
sir, like how is it calculated? How is the tonnage factor calculated for each of
No,
the?
you have to take the sample to the lab, right? To estimate, what is the quantity of ore there.
Okay, okay, sir.
Yeah. So when you dig this boreholes, you take the sample out, right, for the analysis.
Yes, sir, got it.
Yeah. Okay. So then there is something called rule of nearest point. Okay. So these are the like these we discussed about the triangular method. So we have the rule of nearest point. Please go through, read this one. I'm just explaining what is this. So let's say we have some points here. These are the boreholes, randomly planned boreholes. So why it is not in a regular pattern? Can you tell me? Like, is it possible that it will not be regular? Anyone? Did you understand my question?
So can you please repeat the question?
Yeah, so I said these are the boreholes, from where we took the information. So these are sometimes not uniform, right? Like it can be perfectly in this regular kind of pattern, in a square pattern or rectangular pattern. So sometimes it is not. Can anybody tell me why it's not?
So because the contours, like it is not
Yeah.
really visible.
Yes, not possible to take the drill rig, right?
Yes, sir.
Okay, very good. So in this, in this method, what we do is we just try to connect two boreholes using some line. Okay. So the nearest boreholes. So and then what we do, we get the perpendicular bisector here. So to bisect these lines. Okay, and this is the bisector. Similarly, or maybe I can change. So this is the bisector line. Similarly, this is the bisector for perpendicular bisector for this. So this is the perpendicular bisector for this. This is the perpendicular bisector for this, and maybe this one is the perpendicular bisector, and this one. So can you see? We create a polygon like this. Okay. So in that case, what we do that this whatever this grade and thickness we have here, that we think that we assume that this is applied to this total area. Is this clear how we did that? Anybody who could not understand?
Sir, can you repeat again?
Yeah. So what I'm saying is, this we just first thing is we drill these holes, right, and took the cores out and got the grade and thickness at different locations. Okay, and then we want to calculate what is the total amount of the ore in this area. Okay, for that what we can do is, this is the rule of nearest point. What it says is, let's say this is the borehole we are looking at. Okay, so for this, what you are going to do is we just join these lines. Oops. So between the two nearest boreholes. Okay, so join these lines, join this line, join this line, join this. Similarly, like this. Okay, and you try to get the perpendicular bisector of these lines. So the perpendicular bisector are these, the green ones. Bisector of these line. Okay, similarly, bisector of this line is maybe going like this, and this is going like this, and this is going like this. Okay, so this is the polygon that has been formed. Okay, so to calculate what is the total quantity of ore in this polygon, you just assume that this is this borehole is representing this polygon. Is this clear?
Yes, sir, got it.
Okay. So let's say you have a rectangular pattern here. So in this case, let's say you want to calculate what is the, in this case, what you do? You just join these lines, right? The nearest points. And this will be again a rectangle. Okay. So the grade, this let's say this is L and this is D. So the quantity of this ore, or maybe total quantity of this ore in this polygon, will be L times D into thickness here T, and if this is grade is G, T times G will be the total quantity of that the ore. Is this clear? Anybody?
Yes, sir.
Okay. Okay, so this is another method, right? And this is the last one we will talk today. So it's something called block model. Okay, so about this block model.
So in the last one, L was the length and D was the diameter.
Yeah. For this polygon is a rectangular, like rectangle here, right? So it will be divided in rectangle in all around this thing. So L is the length of this rectangle here. D is the, I don't know, this length here, right? Or maybe width of this rectangle, and that's why this length into width into thickness into G will be the total quantity of the ore.
Fine, sir.
Okay. Yeah, these are simple techniques. So last one, what we use this today is, we use the computers. So this is something called block model. So what we do is, as I said, we use computers. Because if there are n number of these boreholes, then calculating all of them takes a lot of time, right? So, and what we do here is we make a three-dimensional area block. 3D array of blocks. Okay, so how it looks like is, yeah, this is what it is written. So this is, let's say this is the, this is the deposit here. Okay, so we divide the whole area in these three-dimensional area of blocks. So maybe these are small cubes or rectangles, right? Those are there. And we try to find out what is the average grade in each of these arrays, or each of these arrays of blocks. Okay, small block, what is the average grade that we try to find it out. Okay, so and this is done using two ways. First is nearest point, directly take the nearest point sample. So if you have a block here, and let's say this is in 3 dimensions, this is the location of the borehole, right? And this is the closest one. So if the grade is G, or maybe 0. Let's say 6, so this will be assigned to this block. And this will be assigned to this block also, like whichever is the closest one. That grade you directly assign to that block. Okay, so this is the nearest block value it takes. Second thing what we do is we take the weighted combinations, right? So with some radius of influence. Okay, so and one of this method, like this method, I'll be explaining about this, is called inverse distance weighting scheme. Weighting scheme. Okay, what does this mean is, let's say any block we are going to consider here. This is the block. Okay, so that is that block we are talking about here. So what it does is, let's say that is the location of this block. This is the block here, and around this block there are different boreholes, and starting from G1 is here, right? Can you read this thing? This is too small or
So fairly visible.
visible? Okay, so yeah, So this is G1, similarly G2, then G3 is somewhere, I don't know, where's G3? Okay, so G3 is here, or this G5, G4, or something like that, right? Whatever it is. Okay,
Yeah.
maybe G3 is here, see? So what we do here is, we define something called radius of influence. So we say that, okay, after this much distance, if the distance is more than 60 meters, I'm not going to take those borehole data. So let's say these are the boreholes which are falling within that radius. So you have the center of the block, you make a sphere kind of thing, or maybe circle kind of thing, and which is falling, those boreholes which are falling within these within this radius, that you will consider. And this is what it is shown here. So this is the center of this block, and let's say for G7, the grade is 1% and the distance is 250 feet. Okay, similarly for D6, this is 200 feet and the grade is 0.5%. Is this clear up to here?
Yes, sir.
Then I said that we have something called inverse distance weighting scheme. So what is this is given by this equation. So in here, let's say you want to calculate. So let me zoom it out a little bit. Oops. So the average grade G for this block will be D average equal to G2 into 1 by D2 square. G1 is not within this limit, right? So that's why we neglected 1 by G2 into D2 square plus G6 into 1 by D6 square plus G9 into 1 by D9 square plus G7 into 1 by D7 square plus another one is G4. G4 into 1 by D4 square. Okay, whole divided by 1 by D2 square plus 1 by D6 square plus 1 by D9 square plus 1 by D7 square plus 1 by D4 square. Is this clear? So if you know all these values, you can easily calculate what is the average grade for this block.
So why we didn't consider the G5 and G3 thing?
As this is how we are defining. This is based on experience. So maybe that is not coming within this. Maybe it is coming within this radius, but again we are defining some area that's just lying on the radius, or maybe within few meter. We are not going to consider. Okay, so we are defining those kind of things. So that decision is based on your experience.
So how
Okay,
do we
so
name the values like G1, G2? How we are naming the G1 and G2s to
it's
G8?
a kind of random location of the boreholes. So these are fixed, So maybe another block is somewhere here. The second block. It will be continuous blocks, right? Okay,
Yes.
everywhere the blocks are there. If you see this picture, so just a second. Yeah. So everywhere the blocks are here, right? Like if you see the blocks written C here, let's say we are talking about this block. So we have another block here. Then it will find out what are the boreholes around it. Is it coming within my radius? If not, then you'll neglect that boreholes. So maybe there are hundreds of boreholes all around this. Okay, there are more boreholes all around this. We are neglecting those. Okay, because this is not coming within our radius. Is this clear? So let's say another block we are considering is here. So this around this block, maybe if you make a circle, maybe this borehole will come, this borehole will come, this borehole will come, this borehole will come. Similarly, all for these, all you will change throughout your, your volume. I mean, right? Continuously change those locations and to calculate what is the average kind of grade. Is this clear? Yeah, please let me know.
Yes, sir. Sir, so what are the things that the ROF value will depend on? ROI, radius of influence.
I think it is how much it is varying, right? How it is changing. If you change, let's say instead of the 60 meter, I made it 160 meter. Okay, so if we make 160 meter for iron ore deposit, maybe it is going to help us, right? Or maybe not good for gold deposit. Okay, so maybe for gold deposit we should make it 10 meters or 20 meters. What kind of deposit it is, and how how far it how easily it changes the grade, right? So those kind of things it depends. Actually, I am not an expert in this thing. Maybe if you take um, if you take some mind planning course, you'll study. But the basic concept is this.
Okay, sir.
Okay, but maybe but it is depends upon your how quickly your this grade is changing, so that you are defining that radius based on that. Okay, let's stop it here. We can quickly revise what we studied. So this is a simple thing we learned, right? So about how we calculate using simple techniques the total quantity of ore in a deposit, right? So next class we'll be talking about something called geostatistical method. Okay.